Okay, hello, and welcome to lesson 5.2. So, I'm going to split this lesson, I think, into two parts. Actually, I don't even know if I'm going to make the part two. um, in class, I talked quite a bit about the history of complex numbers and where they kind of come from, or at least the mathematician who first acknowledged their existence, as this is what the lesson is over today, over complex numbers and a reminder on simplifying radicals. So before I really begin on anything, the primary focus of this lesson, there's two objectives. First, you need to be introduced to imaginary numbers because it is finally time to acknowledge them. We could have acknowledged them earlier, but I don't know. It's just very common to finally learn about this in Algebra 2. And we're going to talk about what an imaginary number is, as it is a solution. You can have imaginary solutions to things involving radicals. The other piece is simplifying radicals as a sort of review, also used in tandem with complex numbers, because all of this is to support our solving of quadratics in lesson 5.3. In lesson 5.3, we're going to talk about completing the square and the quadratic formula, both of which use square roots. And simplifying these square roots is a necessary skill. We have to be able to simplify these square roots. So all of this, you can think of this just as a workout for your brain. You got to get good at this because these are the mechanics, right? These are the motions of solving. You have to have this stuff down. Otherwise, it's going to slow you and you won't be able to really solve a problem because it's kind of just the tedious, right? The tedium of a problem solving. So anyway, let's get started. Now I'm going to introduce complex numbers and explain what they are here, but I'm not going to give the historical component in this video. So I'm really just going to brush through it very quickly and not spend a whole lot of time explaining what they are exactly. So real quick, I have a little review on the types of numbers. So maybe in 7th, 8th grade, something like that, maybe in 6th grade, you've talked about what types of numbers there are. First, we talk about natural numbers. These are counting numbers, 1, 2, 3, 4, things we count, right? The next set of numbers is whole numbers. These are natural numbers, including 0, so it's just 0, comma, 1, 2, 3, 4, and so forth. We make this distinction, excuse me, we make this distinction because natural numbers, well, without including 0, there are certain properties of the natural numbers, things that we wouldn't do with 0, that help us define, well, math, I guess you'd say. I mean, if you take a number theory class, these distinctions between each of these types of numbers, whether you want to call them rings or fields or whatever they're called, that's when this stuff gets really, really important. But for us, I mean, more or less, it's just for fun. Then we move on to integers, which are whole numbers, but positive and negative. Then next we have rational numbers. Sorry, I'm getting a little sleepy here. Rational numbers, which are numbers that can be written as a ratio, you see the word ratio in rational, of two integers. Now this is important. It's important that it's the ratio of two integers. A lot of times people say this is just, it's rational numbers are just fractions. Not quite. It's a ratio of two integers. It's a fraction where they're integers on top and bottom, like 2 and 3. Then you have irrational numbers, numbers which cannot be written as a ratio of two integers. So these are things like pi and e, or square root of 2 is a famous one. These are irrational numbers. They don't have a terminating decimal. Their decimals go on and on and on forever because they can't be expressed as a ratio of integers. Now, think about the number pi over 3. Is this rational or irrational? It's irrational. Just because it's a fraction doesn't make it rational, right? Pi over 3. Well, pi is not a ratio of two integers, so pi over 3 can't be written that way either. Okay, now on to the new stuff, because that was really just review. We have a new number type, and that is called imaginary numbers. Now, imaginary numbers are the square roots, or you can think of even roots, of negative numbers. So, square root negative 12, square root negative 3, square root negative 5. And when I say even roots, this could be fourth root of negative 16, sixth root of negative 2, eighth root of negative 1, right? All of these are imaginary numbers because I can't find these roots and have real, excuse me, so sorry. Can't have real numbers. All right. So here we go. Let's talk about these imaginary numbers, and this will be very quick. The imaginary unit, meaning the most basic imaginary number, is written as I equals the square root of negative 1. Okay? That's pretty much it. So instead of writing square root negative 1, we will write I instead, because that is what I represents, as square root negative 1. All right. Now, I'm using the word imaginary to indicate the square root of negative, but another word we could use is complex numbers. So, complex numbers are really the whole field of numbers. It's all the numbers. It's real numbers and it's non-real. So when you see this word imaginary, you can think these are not real numbers. These are non-real. We could call them that. Complex numbers are everything. Now, complex numbers are written in standard form as A plus BI. This is how we write complex numbers, where A is a real number and BI is an imaginary number. Okay? So B times I could be an imaginary number or imaginary component. The B value can be a real number. So, for instance, 2 plus 5i. 5 is a real number, but 5i is an imaginary number because it has that imaginary component. So let's look at a couple examples of operations with complex numbers. I didn't even bother writing these. Silly me. Let's do 2 plus 3i minus 6 minus I. I just made that up on the spot. So this first example is really simple. Think of this as combining like terms, right? This is absolutely no different from combining this expression if the i's were replaced with x's. No different. You would distribute the negative and say 2 plus 3i minus 6 plus I, because the double negative, and then you just combine like terms. 2 minus 6 is negative 4, and 3i plus I is plus 4i. And that's it. That's operations with complex numbers. So it's just combining like terms when you do addition and subtraction. All right. What's a little bit more interesting though is something like this, multiplication. Let's do 3 minus I times 2 plus 5i. Now, this is going to be a multiplication operation. So let's distribute this. I get 3 times 2 is 6. Here, if we want to remember, FOIL, right? FOIL. Now, let's do this. 3 times 2 is 6. Then 3 times 5i is 15i. And then negative I times 2 is negative 2i. And then I have negative I times 5i, which is negative 5i squared. So you could do 6 plus 13i by combining those sliding terms, then minus 5i squared. But hold on. We said that complex numbers, and this goes for all numbers, can be written in standard form as a plus bi. See that? See what I've been circling? That's I squared. Standard form doesn't have I squared in it. It's a real number plus a bi imaginary number. There is no I squared here. So, what do we do with it? What do we do with it? Because this isn't actually in standard form. Well, what is I squared? I equals square root negative 1. So then I squared equals the square root of negative 1 squared. Therefore, I squared equals what? Think about it before I write it. If I square a square root, I'm just left with that. So I'm going to circle this. Ooh, pretty circle. So therefore, I squared equals negative 1. So if I'm going to write this, I can replace 6 plus 13i minus 5, and I squared is negative 1. Therefore, this negative 5 times negative 1 is plus 5. So this is a real number. 6 plus 5 is 11. And it's 11 plus 13i. And there you have it. That is our standard form imaginary number. Standard form complex number. The real and imaginary component. Yeah. So we can, by using powers of exponents, jump from imaginary to real again. And that's useful and important. Okay. So that's the basic operations. Addition and multiplication. I'll tell you, they love to throw multiplication problems on standardized tests, like SATs and whatnot. Every now and then, it's one of the beginning few problems, like the first 5 or 6. I don't really know why, but they like to do it. They want to see if you know what complex numbers are. All right. Now, before we move on to simplifying radicals, I did want to observe the powers of I, because these are really cool. And they're how do you say? I don't know. They're just cool. That's all I want to say. They're just neat and interesting. So let's look at I. I, we said, was the square root of negative 1. And we said I squared was negative 1 because we squared that, right? So what is I cubed? Well, I cubed is I squared times I. So that's just negative 1 times I, which means I cubed equals negative I. So this is negative I. Then let's look at I to the power of 4. I to the power of 4. We could do I cubed times another I, or I like to think of it as I squared times I squared. And I squared is negative 1, and the other I squared is negative 1. So you multiply negative 1 times negative 1, you get positive 1. So I to the power of 4 is positive 1. Now, if I take I to the power of 5, that's just I to the power of 4 times I. But that's just 1 times I, which is just I again. And so I get I here. Now, you can keep going, but really what's happened is you have circled back to here, right? Here, let me make that nice and curved. You have circled back. It's a cycle. cyclical. Because I go back to I. So when I do I to the 6th, that's going to be the same as I squared. So let's take a look, right? Let's look at example 3 here, right? I to the power of 7. You will need to use your, what do you call them, guys? Your exponent rules. So actually, I'm going to pull that out real quick. Exponent rules. So a couple of exponent rules say a to the m times a to the n. Whenever I'm going to write these nice and big so you can see. Whenever I multiply the same base, I add their exponents. So example, x squared times x cubed is x to the power of 5, because 2 plus 3 gets you that 5. The other rule, I'll call that one. The other rule is a to the m raised to the power of n equals a to the m times n. So your example is let's call it x squared. Then that quantity cubed is x to the 6, because it's 2 times 3. We need to use these exponent rules to manipulate powers of I. So use to manipulate powers of I. Also, you might be wondering, what are we doing? Why? What is with this I business? Why even fiddle with I? What is this? Who came up with this? Well, you can watch my little history video if I decide to post it. Or you can Google it. You can, take learning into your own hands. It's useful for higher math. Very higher math, okay? Not so much useful just by on its own, but it has a lot of applications in big boy math, just big college post-calculus math, all right? Post-calculus. Okay, so let's look at I to the power of 7. If you use the first exponent rule here of addition, well, I to the power of 7 is like saying I to the power of 3 plus 4, which can be split up as I to the power of 3 times the I to the power of 4. But then I to the power of 3 is, I to the power of 3 is negative I, and I to the power of 4 is 1. So this is like negative I times 1, which is just equal to negative I. And done. I like to make those perfect boxes. You know what I mean? I like to make those nice, beautiful, perfect boxes. Thank you, iPad. I love you. Okay. Now let's look at I to the power of 55. And the key here, really, is looking at I to the power of 4. This is super useful. I mean, you can use the other powers. It'll help. But I to the power of 4 is the most powerful. Powerful. Anyway, because when I multiply stuff by 1, it doesn't change. So that's really easy to do math with. So take a look at I to the power of 55. The way I do this is look for the closest number to 55, to this power, that's divisible by 4. That's below 55. You could do above, because you can say, 56? But I would caution, because you don't depending on your experience, you may or may not know negative exponents yet. And if you don't know negative exponents, then don't do that. If you do, all the more power to you. Oh, again, all the more power to you. Oh my goodness. The puns right now. Okay, so I to the power of 55 is I to the power of 52 plus 3. Yeah? So then that is I to the power of 52 times I cubed. But 52 is divisible by 4, right? Let me think. 52 divided by 4 is 13. So this is like saying I to the power of 4 times 13 times I cubed. But using the second rule, a to the m equals a times n, or a to the m times n, this expression for I can be written as I to the power of 4 raised to the power of 13, since those exponents are being multiplied. And then this is times I cubed. But of course, I to the power of 4 is 1. So this is 1 to the 13 times I cubed, which is just 1 times I cubed, which equals I cubed, which we said I cubed equals negative I. And we got that answer again, I guess. I guess I should have picked something like a little bit better, but whatever. This gets at the same idea. All right? Oh, the same idea. The same idea. Oh, power. That's fantastic. All right. And those are my examples for powers of I. They love to throw this on all sorts of tests because it really assesses your exponential manipulation, and whether you understand powers of I. Okay. All right, let's move on. I'm sorry, I'm not the most enthusiastic about this lesson because it's just kind of like well, I'm not going to say remedial, but it's just like, I don't know, it's the basics. It's the little exercise. Okay, look, think of it like this. If you're a musician, right? Your instructor probably told you should play your scales and arpeggios, right? Is it fun playing scales? No, scales suck. I was a musician. I hated playing scales. They're not fun, No. A, B, C, D, E, F, G. Repeat, right? Not fun. But by practicing your scales and practicing them well, it ends up improving your performance as a musician, right? I mean, it really, really does. So if you get really good at your basics, even though they're a little mundane, even though they're a little bit boring, they make you really strong. All right, it'll make you a really strong mathematician if you get strong in these basics, okay? So just trust me on that. Okay, so simplifying radicals. Now this is more or less review. It probably deserves its own video, but I don't care. I'm just going to keep going and just power through. Now, the idea of simplifying radicals is you're looking for a particular root that you can take. So let me just explain this. We're mostly going to be talking about square roots right now because the unit is focused on quadratics. In quadratics, we're going to be doing square roots. We'll come back with cube roots and whatnot, higher roots in the future when we talk about our own radicals unit. But for today, we're just focused on square roots. So because I'm dealing with square roots, I want to look for perfect squares. Now, before I do any of this, a rule to know. The square root of a times b equals the square root of a times the square root of b. This is one property of radicals. You could also say that the square root of a divided by b equals the square root of a over the square root of b. These are both true, okay? And you can use these anytime you need. These rules are just these are exponential rules hidden in disguise, and we'll talk about what that means later. Okay, so 24. Do you know perfect squares that divide into 24? Well, 4 times 6 is 24. And then by using what I've starred in blue, I can separate root of 4 times 6 as root of 4 times root of 6. What is the square root of 4? It is 2. And then this is 2 root 6. And so I am done. Now, how do I know not to go further? Well, square root of 6 is equals square root of 2 times 3, but you can't go any further, right? Can't take out any more perfect squares. I can't write. Perfect squares. All right. Can't take. Okay? All right. Okay, let's move on. This is basically what you're doing. You need to know your perfect squares, okay? I'm sorry, you're an Algebra 2 student, especially if you're an advanced Algebra 2 student. You got to know your perfect squares. I'm sorry, no ifs, ands, or buts. You got to know them, all right? 288, let's divide that by 4. Oh, look, I get 72. Well, I could probably do better than that. Let's take 288 and divide it by 16. Oh, I get 18. So, okay, let's try that. Well, you know what? For the purpose of notes, let's do 4. Okay, fine. 288 divided by 4 is 72. Okay, look. That is 4 times 72. Now, are there any perfect squares within 72? Yes, there's a 9. You could say that this is square root 4 times square root 9 times 8. Because 9 times 8 is 72. So then this is, the square root of 4 is 2 times the square root of 9 times the square root of 8. But 8 is 4 times 2. So then this is 2 times the square root of 9. That's 3 times the square root of 4 times the square root of 2. Which is 2 times 3 times 2, because the square root of 4 times root 2. So let's multiply that all together. 2 times 3 is 6 times 2 is 12. Equals 12 root 2. Done. There it is. Perfect. And I found it. And that is simplifying a radical. If you need help with this, please come see me. This is a Algebra 1 topic, so you need to know it. Okay? All right, let's move on. One more. This one's nice because we get to do one with a complex number now, with an imaginary number. Now, immediately, right off the bat, I'm looking at 175. If that was $1.75, well, how many quarters is that? 7 quarters, right? So that means 25 times 7 is 175. So here's how I want to break that up. Equals, I'm going to say root of negative 1 times 25 times 7. So this equals root negative 1 times root 25 times root 7. Root 7 can't be reduced anymore, but this is just I times root 25 is 5 times root 7. So if I write this and finalize it, it is 5I root 7. Done. Get my nice rectangle. Fantastic. Okay, that's simplifying radicals. That's more or less just review, but I wanted to have just a little video resource to come back to as a brain refresher. Okay? It's just a brain refresher. All right. Let's take a look now at rationalizing the denominator. Both of these skills, what I've done in red, simplifying radicals. When we use the quadratic formula or when we complete the square, we will need to simplify the square root of whatever we're taking. So this is where we do this. And then sometimes, depending on how you complete the square, you may have to rationalize the denominator. Now, sometimes it's fine because it'll be a perfect square and every life is wonderful and everything's happy. But sometimes you get a irrational number in the denominator, which we don't want. And you might say, why don't mathematicians like that? And I say, I don't really know exactly. I should probably Google that sometime. But honestly, I agree with them. I don't like it either. What does division by irrational numbers even mean? That's just weird. I'm betting that the reason mathematicians don't like it is a geometrical thing. Because when you think about division is divided into parts. And it really doesn't make sense about dividing something into parts that are, well, not like rational. I don't know. It just doesn't make sense. It's just weird. Okay, anyway. 1 over root 3. How do I rationalize this? This is just a reminder again. So the way I rationalize this is by multiplying by that rational number that's in the denominator. But, of course, I'm going to do this on top and bottom like so, like this. So when I do root 3 over root 3, well, any number divided by itself is 1, right? So that division is fine. I'm not changing the value here. So actually, you know what? Let's draw an arrow so that for the notes we can see it. I'm going to multiply by root 3 over root 3, which is going to yield 1 times root 3 is root 3. And on bottom, root 3 times root 3 is 3. And that is it. That's it, okay? Multiply by that on top and bottom. All right, let's move on. Example 9, I've got 10 over root 50. So I'm going to take 10 over root 50. Now look, you kind of have two options here. You could simplify the root 50 first, or you can just multiply by the root 50 and then simplify. It does not really matter. It's not really a big difference. I'm just going to multiply by root 50 over root 50 simply because I want to. So then the top is 10 root 50 over 50. But 10 over 50 can be reduced as 1/5. So this is like root 50 over 5, right? 1 root 50 over 5. But then root 50 is root 25 times 5 over 5, which is just root 25 times root 5 over 5, which is 5 root 5 over 5, which is root 5. So think about that. I mean, look at 10 over root 50. Do you really want to write it like that? Or is root 5 prettier? Come on, root 5's totally prettier. Look at that. It's beautiful. It's just beautiful. Way prettier than 10 over root 50. Okay. So that's rationalize the denominator, and that is that reminder. Okay, last thing. Gosh, this is a long video, and I hate how much I had to talk today. I'm sorry for that. Maybe in future years of teaching, I won't have to talk so much. All right, last one. And this is the idea of a conjugate. Anybody taking Spanish? Conjugate those verbs? Okay. Not really the same thing, but it's its own meaning in math. So, The conjugate of a complex number a plus bi is a minus bi. You essentially flip the sign of the imaginary component. Notice it's not negative a minus bi, it's just a minus bi. The real number piece stays the same. It's only in the imaginary component that is flipped a sign. Why are we bothering with this vocabulary? Well, the conjugate of a complex number can be used to rationalize a denominator or turn an imaginary number into a real number, so long as you're keeping things balanced, right? Also, you can use this idea of conjugates to rationalize denominators, which have irrational and rational components. So, similar idea. You can use this for more than just imaginary numbers, and you will. I don't remember at the moment with how useful this is in pre-cal. Oh, but I remember how useful it is in calculus. So that's why we're covering it here, so that when you encounter it in calculus again, you may not remember this 100%, but because you've been exposed to it, because you've seen it in action, it'll be much easier to relearn in calculus than learn for the first time. Okay? All right. Let's look at example 10. So here's what I'm going to do. I am going to identify the conjugate of 3 minus 4i is 3 plus 4i. I will multiply by the conjugate on top and bottom. The exact same way I rationalize stuff. So then this is going to become 5 over 3 minus 4i times the conjugate, 3 plus 4i. And I'll put those in parentheses. 3 plus 4i. Now, when I do this, here's what I'm going to do. Let's FOIL the bottom. 3 times 3 is 9. 3 times 4i is positive 12i. Negative I, 4i times 3 is minus 12i. And negative 4 times positive 4i is negative 16i squared. But if you notice, this is just 9. These cancel. And then I've got minus 16i squared. But we said that I squared was negative 1. Since I squared equals negative 1. So this is just 9 plus 16, which equals 25. So the denominator, let's I don't know, 25. I'm going to say, okay, so the top is 5 times 3 plus 4i over 25. That 25 right there. Okay? Can I make this nice? Okay. But, of course, this is just 5 times 3 plus 4i over 5 times 5. So those cross out, and I am left with 3 plus 4i over 5. And ta-da! I have, in essence, rationalized the denominator. Look, you might be saying, why? Who cares? Just trust me, all right? Just trust me that this is useful and important in a calculus, pre-calculus setting. And higher math, of course. So, there it is. Okay. Oh, man. that was a long video. That took the energy out of me, and I yawned quite a few times. But it needed to be done. We needed to get through it. It was a lot of material, and now we can rest. Take a break. Go get a drink, right? Get a drink of water. Take a soda or an orange juice, something, a nice cup of tea, and just relax for a moment. Let it all sink in. Okay? All right. I'll see you guys later. Hope you enjoyed.